All right, I guess we'll go ahead and get started. Welcome everyone to our last presentation of our second day of TWSS, the TechX User Worldwide Simulation Summit, our user conference. Tonight we have David Smithe speaking, and Dr. Smithe has actually been with TechX for over 15 years, using Vsim on particle simulations, microwave sources, and fusion heating problems. I just want to make a brief announcement too. If you have any questions, you can type them in the Q&A box at the bottom of your screen, and then we can answer them at the conclusion of the presentation. All right, David, I think it's for you.
Okay, thank you, Colleen. Could you verify that you can hear me? Yeah.
I can hear you just fine.
Okay. Well, thank you to everybody who is attending. Some of you are in your evenings and a few of you are in your morning. Today I'll be talking about using Vsim to model THz microstructures and plasmonics in gallium nitride two-dimensional electron gases. You'll hear, I'll say 2DEG's for the rest of the talk, but that stands for a two-dimensional electron gas, which is used in, transistors for high electron mobility devices. The talk will proceed. I'll talk first actually about plasmonics, and then we'll work our way up to some microstructures. So this work was done as part of an SBIR project, so as part of the commercialization, I get to do some practical stuff. So this talk is hopefully a sneak peek at some future examples and some new capability. So let's get into it right away. At terahertz, there's a problem. Transistors don't work anymore. So we cannot use transistors as good amplifiers. We can't get gain. This is the traditional picture you see. Here's a frequency scale in gigahertz. So 1 gigahertz is over on the left, 10 gigahertz, 100 gigahertz, 1,000 gigahertz is a terahertz. And you can see that the transistor gain falls off to 0 almost exactly at 1 terahertz. So what do we do? So that's the source of our terahertz gap in terms of microwave sources. What is going on? Why does this happen? It's fairly easy to understand. In the transistor, we're no longer in a drift diffusion situation. We start picking up plasma effects. I'm a plasma physicist, so that means I can finally start to play with the solid state at this point. And so beyond our transistors, we talk about plasmonics and maybe some new microstructures, and that's the subject of this talk. So this is what's going on. If we, I like to use gallium nitride as my reference because that's pretty much the best sort of real world two-dimensional electron gas we can work with. In the two-dimensional electron gas, we have high mobility, higher than in the bulk, say 1,700 centimeters squared per volt seconds. You can turn a mobility directly into an effective collision frequency just using the mass of the electron and the charge of the electron. And it comes out to be almost exactly 1 terahertz. If we just look at the standard force equation, so dV dt is charge over mass times electric field with a collision drag term here. In traditional electronics, it is the drag term matching the electric field. This is the drift behavior. The dV dt is actually neglected because it's slow compared to the collision frequency. But you can see that when nu is around 1 terahertz, and if I have an oscillation signal around 1 terahertz, then these two terms are now equal. We can no longer ignore this term. We'll call that the inertial term. And so when dV dt balances E, then you get very different physics from when the collision frequency balances E. So when omega is much, so to summarize, when omega is much, much less than nu, that's frequency less than collision frequency, classical drift physics dominates. When omega is much greater than nu, then inertial physics dominates. We are at 1 terahertz and 1 terahertz. We're right at the transition where drift behavior fails and inertial behavior picks up. And that is the subject of this talk. So when the inertial terms dominate, you get plasma oscillations. For this talk, we're not really interested in 3D bulk plasma waves, which are stationary waves, or if you add a temperature, you get a Langmuir wave. We're actually interested in plasmas that are a sheet of plasma, a two-dimensional electron gas, which is what occurs in a thin layer just above the gallium nitride. This means in our analysis that instead of our plasma frequency being a certain number of electrons per meter cubed, it's actually a certain number of electrons per meter squared. So what happens if we try to calculate a plasma frequency with a number per meter squared? Well, we're missing a unit of length there. And the only place to pick up a unit of length is the wave number. And so plasma frequencies for a two-dimensional electron gas follow this formula. Omega squared goes as not just density, but now it's two-dimensional density divided by, or times the wave number, K. So if you think about this, this is now an omega going as K. So this is now a traveling wave instead of a stationary wave. And if we just divide by K, we get the phase velocity of the wave, which goes as the two-dimensional density either divided by the frequency or divided by the square root of K. And so this is true of any two-dimensional electron gas, whether it might be a vacuum plasma or a solid state plasma. However, vacuum plasmas have very low densities, and so this velocity is very small. In solid state, we have very high electron number densities, and so that's where this starts to become very interesting. So I said that this is a traveling wave. Well, how fast does one of these plasma waves go? If it's a gallium nitride, we might have a two-dimensional number density of about 2 × 10⁻17 per meter squared. We've got a dielectric constant of about 3.4. You plug that into the formula, and remember it goes as 1 over frequency. So you get at 1 terahertz, that's this point right there, you get something going about maybe 1/20th the speed of light. And that's really fast because remember, particles in solid state are moving at 10 to the 4, 10 to the 5 meters per second. And so the wave, the plasma wave itself, travels much faster than the particles themselves. And because we're within an order of magnitude or 2 of the speed of light, that means we can start thinking about coupling electromagnetically instead of the usual electrostatic drift diffusion type behavior. Well, all good science is, you know, some fun and some math. So we'll have a few slides of math here. So this is what we're working with in terms of our two-dimensional plasma waves. We've got a sheet current density, which is minus En2D. We're going to allow ourselves a drift velocity, V0. Now, this is typically a solid state drift velocity, again, in the 10 to the 4, maybe 10 to the 5 meters per second. Nowhere's close to a vacuum electronic beam, which might be near the speed of light. So this is a very small velocity. Collision frequency, temperature, DC electric field, and then our perturbed electric field, E1. This is a linearized analysis. So we have a continuity equation with our solid state current density and our solid state charge density. And then we have a force equation for our solid state current density, which is basically rho times E. However, we do have some drift velocity. So we have an advection term, a compression term, and a density term. The usual equation actually ignores all the black terms on the left and just has the collision frequency. And this is the diffusion term. So here's your drift and diffusion, your inertia, your compression, your advection. Then we'll also have a DC electric field. And so we have rho naught E1 and rho 1 E naught. And so those are the equations we're working with. Those J's don't work because they're three-dimensional current densities. So we've got to convert from amps per meter squared to amps per meter sheet current, sheet density. Do our usual Fourier analysis. And well, you can see we've got 2 omega minus k's in these two equations. And so we can work these equations out. Here you'll get your omega minus kz squared. And what we'll do is we'll put the electric field in terms of the sheet current. And so that is our continuity and force equations give us this relation between electric field and sheet current. We'll need a second relationship between electric field and sheet current. And of course, electrostatics, that's Gauss's law. If you just, these are simple two-dimensional problems if we ignore the third dimension. And so you can practically write down what the electric field is. It's going to be exponentially decaying away from the sheet of current. And then, of course, it'll have sinusoidal behavior, e to the I kz. And so then this gives us a second relationship. We'll convert charge current to, or sigma to K. And this will give us a second relationship between electric field and kz in sheet current. And so you combine those two and you get a dispersion relation, nothing too fancy there. This is basically our dispersion relation. What's different now is where we used to have our usual E squared M over ME, it's now an N2D. Doesn't really work as a plasma frequency anymore. You can cast it a little more easy or as that drift, as that wave velocity that I was talking about, instead of the plasma frequency squared. And so then your dispersion relation is basically omega going as the square root of kz, as we saw before. This time I have a little bit of drift velocity there. And you can compare this to a 3D bulk oscillation, where this would just be a single fixed number that only depended on density, but now it depends on density times wave number. What does that look like? Well, if we had a drift velocity like a vacuum electronics beam, we would have one of these blue lines, and then the plasma wave splits that blue line into two very close lines. And then one of those blue lines would say intersect with maybe some kind of slow wave structure. represented by the dotted green line. Our solutions for our 2DEG plasma wave are these square root K things though. And they actually look like this, quite a bit different. And instead of splitting like this, they split for a positive and a negative K this way. And so the behavior is quite a bit different in this type of plasma wave. Can we simulate these? Well, yeah, that's the title of this talk. So we can simulate these 2D plasma waves in Vsim. And in later slides, I'll show you a little more detail on how that works. But here's one of our earliest simulations of that. We have our planar two-dimensional electron gas right here. We've got some strip lines that come in this way. And the couplers are kind of split into this, what I call a tripole structure. And the idea is we've got current excitation here that travels down the strip wave, excites a wave on the two-dimensional electron gas, which maybe propagates over here and is picked up here in this second strip line at, you can tell, a much lower amplitude. As I said, and actually these blue and green contours are the plasma current, the solid state current in the 2DEG. You can tell we've got some problems here, and I'll talk about this a little bit later. This is not something that we would ever recommend building. These simulations kind of show you that doesn't really work that well. But this was one of our early attempts at modeling these space charge waves and maybe trying to model a way to measure them. So how do we model the plasma waves in Vsim? Well, the two-dimensional electron gas itself is about 10 nanometers thick. It's too thin to be resolved by a finite difference cell size. So we treat it as an infinitely thin plane of current. Now, the current itself, the force equation is just the standard plasma equation. Could we do this, say, from the Vsim GUI? And we probably could, using the linear plasma feature that Daniel talked about in the previous talk, if you were listening to that. And so you could probably go ahead and show the traveling plasma wave straight up from the GUI. Now, that is not what I have done. I am using text-based input, which is the old style. And typically for TWSS, I always give a text-based input talk. No different this year. Why didn't I use the GUI? Well, as I mentioned, we've got drifting plasma. And in the model that Daniel was talking about, there is no drift velocity. And we really need that for what we're doing here. We are kind of playing with boundary conditions, and they're not really well controlled by the GUI at this point yet either. And then the model in the GUI is designed really for magnetized plasmas. At the moment, we're doing unmagnetized solid state device. That makes it a little easier to stick with the edge currents rather than the nodal currents used in that model. So that are three good reasons why we are doing text-based input. Of course, if you do text-based input, you got to be able to read input files, pre-files that look like something like this. This is the full set of update steps used to push the electromagnetic fields and the plasma. A few of these things you might recognize, like the Faraday and the Ampere updaters. Here's some open boundary conditions. The trick here is when we accelerate the J. So this is where we update the J. We'll have accelerate steps. And you can see it's split. We're doing some operator splitting here too to do the drift velocity. And in fact, that drift velocity will use an upwind differencing scheme, which is done right here. So this is the sequence of update steps. We'll zoom on in and take a look at what these accelerate steps are. They're really not too hard. I know this stuff looks bad, looks hard to do, but it's really not that hard once you get used to it. The key updater is where the dJdt goes is the electric field. And that is done with something called a field bin op updater, where we're just adding to the J the incremental acceleration from the electric field. I'll point out that mobility collisions are very important here. And so then there is a factor which includes the collisions here. But these are pretty fast. The field bin op updaters are computationally very efficient. And so this is the key step for modeling the solid state current in this manner. We also had advection. Earlier today, I think the first talk of the day, Jared talked about his fluid model, which unfortunately was still under development when I was working on this. And so I tried to kludge up my own, which beware, fluid dynamics is not easy. So that didn't work. But I fell back to what's a standard upwind differencing scheme. And that worked and that stayed stable. So how hard is it to write an upwind advections operator for Vsim? Well, this is it right here. You'll even see that if the velocity is one way, I use one J, and if it's the other way, I use another. And so here is a poor man's advection operator, just in one little step. We also had updaters there were compression terms, diffusion terms. I have to use row 1, and so I have to update the perturbed density using the continuity equation. And then that row 1 E1 goes in the force equation for J1. And then we are working with several different boundary conditions, periodic boundaries, matched absorbing layer type boundaries, 0J and 0 rho type boundaries. All the boundary condition stuff is still kind of actively being researched at the moment. So what can we do with these simulations? Well, for example, we can verify the dispersion relation. So here is a scan. Each one of these is a two-dimensional electron gas excited over here on the left-hand side. And then you can see there's a different number density, number per meter squared, for each one of these. They all have the same mobility. And you can see the wave gets excited. It has a certain wavelength, and because of the mobility, the wave also damps off pretty quick. And you can see at this lower density, not much going on here in terms of a wave that you can do something with. But as the density comes up, you start to get waves that actually propagate for a couple wavelengths before they damp out. And you can tell the wavelength itself, remember the velocity should go as the density, linearly with the density. And so as the density is increasing, the speed increases, and so the wavelength is also increasing. And so then this is a good test of the analytic theory and basically proves out that in fact that is correct. What else? Well, you can do a little more subtle stuff. You can see that there is actually some two-dimensional effects as the two-dimensional electron gas gets wider. You can see that charge actually kind of accumulates out a little more at the edges than in the center. And that can actually play with your dispersion relation too. We ignored that direction when we did the analysis. And so one of the first things you can do with the code is say, all right, if we don't ignore that direction, what is the edge effect on the dispersion relation. And you can see that as the 2DEG gets wider, there's actually an increase in speed and wave number. So that's a very practical, useful thing to do with our new capability. Could we take this wave and set up a cavity? Here I've got 2DEG suppressed where the mesh is, and then one of these short sections of 2DEG here. Again, I'm exciting it here and seeing if I can ring up a cavity effect, a standing 2DEG wave. I certainly can in the simulations, but the boundary conditions for what happens at the edge of a 2DEG are still not well established. The primary question is, if I've got current that's impacting the edge of a 2DEG, does it bounce off or does it slosh out a little bit? Or what exactly is the condition at the edge of a 2DEG? And again, this is an area of active research and modeling. But our simulations, we do have the ability to model all of these different situations. So as we learn a little bit better what we should do, we certainly will have the capability of doing it. Okay, so that's a description of the two-dimensional plasma wave. What can we do with it? Well, you recall back on slide 12, I tried to excite it. That strip line didn't work too well because if you remember, we had all of those waves that were kind of coming down from it. So basically, if you just try to put a gap in a strip line and use that to couple to the 2DEG wave, to the plasma wave, doesn't work very well. It pretty much mostly just radiates out into space. A gap, after all, is a dipole. So that doesn't work. Now we know that the plasma wave is going a little bit slower than the speed of light. We're familiar with that kind of behavior when we work with slow wave structures and traveling wave tubes, really, in the vacuum electronics world. So we might try to see whether some of those structures taken over from the vacuum electronics world might work to try to couple between a structure and the plasma wave. Of course, the best traveling wave tube is a helix. Maybe we could put a square helix around this sheet of current. There are meander lines we could use, and maybe even a dielectric photonic waveguide. And so these are ideas that we kind of take from the vacuum electronics world and see whether maybe we could bring them over to the solid state world. Here is a very early simulation showing, what basically taken our Helix TWT example, and I took the round cylinder and made it square. I took the round helix and made it square. Here's the input and output couplers where they are, and then would be where the 2DEG is here, with maybe a DC voltage to pull a drift on it. And so this would be, taking this analogy to the extreme. As it turns out, when I simulated this, the square helix is the weak point. It doesn't have a very good axial profile. The fields concentrate on the edges instead of in the center. And of course, if I tried to bring this to a solid state fab, they'd probably just throw me out the door laughing, because it's probably impossible to fabricate something like this on such small scale that you would need. But, it's kind of a start to get you thinking about it. And, even if we can't build it, we can simulate it. Meander lines and interdigital lines, we looked a lot at those. In the end, we kind of found that our best profile for coupling between a slow wave structure and a 2DEG is probably this meander line shape. And the V shape is kind of important. You could have U shapes or V shapes, and the V shape is actually what we need. This really is just a strip line over a ground plane. And so it's TEM-like. The primary field exists between the strip line and the ground plane, and just follows the pattern like that. But the really interesting thing about this structure is the axial field. The axial field decays away exponentially upward above it, but it's got strong field up above it for a significant distance. And the V shape actually manages to peak the field on the axis. And so you could imagine taking this meander line, and then just a little bit above it, you could put one of those 2DEGs, and this 2DEG would sit in the axial electric field that exists above the meander line. So then you have a question of tuning it. If you could tune the wavelength of the meander line to the wavelength of the plasma wave, then you'd expect strong coupling. And in fact, you can do exactly that. That's what we've got going on in this simulation here. So here is a cut through it. Here are my meander line intersections here. I initiate a wave on the meander line, and as it propagates down, it crosses over and converts up to the space charge wave on the 2DEG, which you can see as the second set of contours up here. So this is very exciting. Of course, before you get too excited, I'll let you know that I had the mobility losses turned off in this case, which meant that this plasma wave is propagating a lot further than it normally would. But this shows that you can certainly transfer energy from a slow wave structure into the space charge wave. And we're doing it without radiating out into free space or anything like that. So that's potentially a very effective way of coupling. It's Vsim. You can always make some really pretty waves. So here's a similar thing. You see the initial wave on the 2DEG, or on the meander line down here. And then you see the space charge wave up here. These are E-axial, so the electric field in the axial direction. You can actually see that the space charge wave is running a little bit ahead of that, or well, actually it's probably converting energy from one to the other. But you get a good view of the 2DEG, where it's sitting and what its width is compared to this V-shaped meander line underneath of it. Of course, a meander line is metal. It'll have metallic losses, and metallic losses at terahertz are usually very significant. We've also been looking at using a photonic waveguide. Now, a dielectric waveguide is really a fast wave device, but if you use something like titanium dioxide, which at terahertz frequencies has an epsilon around 100, you can slow that down by that factor of 10. And with a little bit of work, you might be able to synchronize that. Interestingly, the second mode of what's the traditional rectangular photonic waveguide has an axial field pattern that looks like that, with a center. Normally, the first mode has a null on the center, but the second mode has a peak on center. And so you might be able to use the second mode of the photonic waveguide to also couple. to a space charge wave. So that's my talk. So to summarize, we've been using Vsim to look at charge carrier behavior in solid state at these terahertz frequencies where the inertia term starts to dominate the drift term. So we'll just call this plasmonics when that's the case. We're particularly interested in the two-dimensional electron gas geometry since it has a traveling plasma wave. And we're looking at microstructures that could interact with such a traveling wave. So thank you very much, and I'll entertain questions.
Thank you so much, David, as you help us finish out our second day here. So I have a couple questions that was sent to me separately. So the first one is, how do you treat the solid state character of the charges in your fluid model?
So yeah, so this is a fluid model of solid state behavior. Traditionally in solid state behavior, you've got your valleys, your energy valleys. And so really what we're doing is we're using what's called the parabolic approximation. And so instead of the usual electron mass, we use m star instead of m. So for a gallium nitride 2DEG, m star is about 1/5 of the free electron mass.
We have another question. When will these features be made available in a Vsim release?
Well, you can tell that I'm actually doing them with a currently released version of Vsim. The problem is I'm doing it with text-based. There's a bit of work to be done to make them usable from the GUI, the two-dimensional nature, some of the boundary condition work needs to be done. And I probably want to improve on the drift model and maybe use what Jared has done.
Do you have a plan to make an SDF example?
Certainly, yes. I'll get 1 or 2 SDF examples out of this, you know, subject to what I just said in terms of improvements.
Okay. Is there a way to couple the plasma wave into free space terahertz wave?
So, you know, we kind of have played around with these Meander line structures for, you know, specifically either to couple to a free space wave or to, you know, couple to a probe for modeling. So the idea is that you can couple a strip line to the Meander line pretty easy. And so then if you can couple the Meander line to the 2DEG, then you've got your coupling. And then for vacuum, of course, you'd want to couple that strip line into some kind of radiating antenna structure. So there's a number of steps, but the long answer is yes.
For the 2DEG cavity you simulated, what are the boundary conditions?
So what I'm using is that I am setting the plasma current to 0 at the boundary, meaning that there is no 2DEG current once you're beyond that. In practice, you can kind of basically quench or destroy the 2DEG by putting a metal layer over it. Again, I don't really have good confidence in the behavior. So those are good questions.
I know they are good questions. Let's see. So the dispersion of these modes is like that of water waves, square root of a kilogram. So does anything come from that observation? I probably said that.
So let's see. The dispersion is like water waves. I think it's deep water waves rather than shallow water waves. I'm not sure. deep water waves and shallow water have different dispersion relations. I haven't found any useful analogies for shallow water waves. You know, everything can become nonlinear. So far, everything I've done is just linear. So maybe once I start looking at nonlinear behavior, that might become a better analogy to use. It's an interesting observation, though.
Could you use particles instead of fluids to do similar modeling?
We are trying. I actually have some, and maybe that'll be next year's talk. And I'm using our collision models to actually get an accurate representation of the scattering that occurs in solid state. It looks like a mess because the thermal velocities are typically swamp out the oscillating velocity. And so when you do that, it's hard to see anything, even though there's a signal there. But I'm still, we struggle with the Debye length issues in that case. So there was a previous talk on ways of getting around the Debye length. I'll be looking at that carefully. So yeah, particle simulations we're just kind of getting started on that.
For finite difference, 1 grid thickness is still needed. Will that affect the physics of 2DEG?
So I'm putting the current on the plane, on a single plane, and that does not seem to affect the dispersion relation. Actually, when I do the particle simulations, my particles are spread out over a cell, and I am seeing an effect there, and I'm still trying to get a good handle on that. So that's a very good question.
How do you treat the various different scattering mechanisms, like phonon scattering?
So, you know, this is a very classical model, fluid model. So we have what is essentially a collision frequency. So you basically have to take each of your collision mechanisms, like impurity scattering or phonon scattering, is going to have a mobility associated with it. And so we basically turn the net total mobility into a collision frequency. We do occasionally say, okay, let's see what would happen if we were at liquid nitrogen temperatures. And then so that would change, pretty much take us from phonon to impurity scattering and change our mobility. And so we do occasionally change our collision frequency to represent cryogenic situations. But it's really just that single parameter that represents all of that behavior.
Gosh, we have had some great questions. If anyone else has any, while everyone takes a minute to see if they have any other questions, I will just announce that you can see the TechX website listed right there, txcorp.com. If you do not have the latest version of any of our software products like Vsim 11 or Vsim 3, you can go online and request an evaluation for 30 days, and you can try out the software and see if it's something that would work for your problem. We have recorded all of these talks, so they will be on our YouTube page. Hopefully by the end of next week. Our keynote is already up. So if you missed any of those, we've tried to do something a little different this year and hit a couple different time zones, but we realize that means it's hard for anyone to see all of the talks. The last thing I want to say is we did make a change to the schedule. So we did send out an email to everyone who had registered, letting them know, but the schedule tomorrow is slightly different. We moved up some talks. So the talks will be at 8:30, 10, 11, and 12. So just want to give everyone a heads up there. Any final questions? Hey, I think we're good, David. I think we can go end our night.
All right. Well, thank you very much.
Thank you so very much. And thank you everyone for joining us today.